Hello everyone, hope you're all doing fine. Welcome back to another lecture on electrostatics. Since 3 to 4 lectures, we have been dealing with linear charge density and its applications. In this video, we are going to derive the equation for the electric field along the axis of a charged circular disk. And we'll also derive the equation for the electric field intensity at the center of a charged hemisphere. Charged hemisphere. So yes, my name is Vijay Krishna and you're watching UpPhys channel. Let's get started. Okay, now let's read out the title: Electric field on the axis of a charged circular disk. We are going to derive the equation for the electric field intensity along the axis of a charged circular disk. So I have the diagram here. This is the circular disk. Now this is the axis of the circular disk. Okay. Now to solve this, scenario, we are going to make use of surface charge density. Okay. Surface charge. What is surface charge density? Surface charge density sigma is equal to dq by dA, or total charge Q by total surface area A. Surface charge density is defined as total amount of charge distributed per unit surface area. Okay, so this is surface charge density. Surface charge density is denoted with sigma. Sigma is equal to charge distributed per unit surface area. In calculus form, we can also represent the surface charge density, or write the surface charge density as dq by dA. When we take small amount of charge on the surface area dA, then we can write the surface charge density sigma is equal to dq by dA. This equation is valid only when when the surface is distributed, when the charge is distributed uniformly on the surface. Okay. Now sigma is equal to dq by dA. Now from this I can write dq is equal to sigma dA. Now if we use our common sense, how does this disk is made? This disk is usually made of circular rings, right? Circular rings from smaller radius to larger radius, right? So, circular rings altogether is making a circular disk. Now, I'm going to erase this one. Okay, right? So, okay. Now, radius of the circular disk, let it be r. R is the radius of the circular disk. Now I'm going to change the color actually. Okay, right. So circular disk. Okay, now let us take small elemental ring. Why am I taking this small elemental ring? Because this disk is composed of small elements of rings. Here we have one ring, here we have another ring. All these rings are adding together to compose this entire disk. Okay, so I'm going to divide this entire disk into teeny tiny small rings. Okay, now I've taken an elemental ring at here, at so this is the element of ring. Okay, now the radius of this ring is smaller. Let it be smaller. Now this is smaller, and the thickness of this element is dr, is d smaller. Thickness of the element is dr, and radius of the elemental ring is r. Now let us find the electric field intensity. Let us find the electric field intensity at this location. Let this location be p. Okay, now The electric field intensity due to this circular ring along the axis of the ring, which we already know, as I have taken small elemental ring, I'm going to consider the surface charge density. The surface charge density is sigma. Surface charge density is sigma, and the charge of this small element is dq. Charge of this small element is dq. Let it be dq. Okay. So the component that I've taken in the diagram, I've taken a circular disk, which is charged circular disk, whose surface charge density is sigma and its radius is capital R. Radius is capital R. This disk, as we all know, this disk is composed of concentric rings. Concentric rings. So I've taken multiple rings. I've divided this disk into small to big rings. Small to big rings. Now I have taken one elemental ring whose radius is smaller, whose thickness is dr, and the charge on this element is dq. Are we clear till now? Right. Now let us find the electric field at the point of interest P. Point of interest P. Now, as I can observe this diagram, this is the point along the axis of this ring, right? And we know the electric field electric field at a point on the axial line of a circular ring. Axial line of a circular ring. That equation is dE is equal to k q x by r square plus x square whole to the power 3 by 2. This is the general expression for the electric field intensity due to ring along the axis. Now what is x here? This will be our x, this will be our x. And what is q here? Q is the charge of the ring. The charge of our ring is dq. So this dq must be replaced, this q must be replaced with dq, and x, we don't need to replace x as we have already taken the axial length is x. And this r, r is the radius of the ring. Ring radius here we have taken smaller, so I need to replace this smaller as well. So smaller must be placed in the place of capital R. Now the equation would be written as the electric field due to small elemental ring dE is equal to k is constant and q must be replaced with dq, small elemental charge. X is as it is, x comes as it is. Now this capital R must be replaced with small r square and x square whole to the power 3 by 2. So this is the equation for the electric field at point P due to this small ring. Now what I want to find is, I want to find the total electric field. And what is the direction of electric field? In this direction, right? dE. Now if I want to find the total electric field due to the entire disk, what am I supposed to do? I have to integrate. So let's integrate. Okay. Now integral dE is equal to k is constant, x for all the rings, x will remain same. For all the rings, axial length will remain same. So x is again constant. And what do we have? This dq is equal to sigma dA. Sigma and dA. Sigma dA. Sigma dA. Sigma dA. And sigma dA, x we have already written over here, and r square. In the denominator we have r square plus x square whole to the power 3 by 2. R square plus x square whole to the power 3 by 2. What is the variable here? The variable is r. When we look at the diagram, the ring can either be here or here, right? So radius of the ring is changing from 0 to capital R. Radius of the ring is changing from 0 to capital R, right? Now I can use this integration. Okay, I'm applying the integration on both sides. Now let's find out dA, the area of the small element. Area of the small element that I've taken is this one. Element that I've taken is this one, right? And its thickness is dr, its radius is r, radius is r. Okay, now if I want to find the area of this ring, it has thickness and length. Thickness and length. What is the length? If I want to find the area, I can cut somewhere here. Let's say I've cut it here. Then what happens? I can stretch it like this, right? And this thickness is dr and its length is nothing but 2 pi small r. Length is nothing but circumference, periphery. So 2 pi r and thickness is dr. What is the area formula for the rectangle? Which is length into breadth. Length into breadth. So I can replace integral dE, I can write it as E only, right? And k is constant, x is again constant. Sigma can be written as sigma also constant. I'm taking that constant outside. And dA can be written as 2 pi r dr. 2 pi r dr. 2 pi r dr by r square plus x square whole to the power 3 by 2. I think all the steps still here are clear to you, right? Right. Now listen. Okay, now what I'm going to do is I'm going to replace this k with 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught, because k is Coulomb's constant. I can write the equation like E is equal to 1 by 4 pi epsilon naught sigma x 2 pi r by r square plus x square whole to the power 3 by 2 dr. Integrate. What is it? Integral. I have the integration here. Okay, now so as I've already told you, r is the variable here. With respect to r only we are integrating. That means limits comes for r only. What is the smaller value range? Which is from 0 to r. 0 to r. The integration limits would be 0 to r, and here also we have 0 to r, and here also we have 0 to r. Till now everything is clear, right? Okay, now I have this 2 pi here and we have 4 pi here. What will we get? 2. Now E is equal to sigma by 2 epsilon naught. Sigma by 2 epsilon naught. Sigma by 2 epsilon naught. We have x here. We have x here, and we have r by r square plus x square. To solve this integration, what I am going to do is let's assume r square plus x square is equal to t square. This method of integration, we call it as substitution method. What we call substitution method. By using substitution method, I'm solving this integration. So r square plus x square, I have assumed it as t square. Now if I differentiate this one, r square is 2r dr, as x value is same for all the rings. The differentiation of this x square is 0, then is equal to, if t is differentiated, 2t dt. 2t dt. We have 2 on both sides, so they cancel out. 2 cancel out. Now this r dr is equal to t dt. R dr is equal to t dt. So this r square plus x square is nothing but t square. Now I am substituting this quantity and this quantity into this equation, right? We have r dr here. R dr is equal to t dt. I am substituting. We have r square plus x square here. In place of r square plus x square, I am replacing t square. Now if I rewrite this equation, r dr is t dt and r square plus x square is t square whole to the power 3 by 2. As I know, this square 1 by 2 gets cancelled. I will have t cube here. I have one t here, t cube here. We will leave. We will have t square. So let's take it out. Okay. Okay. All right. Now let's use the integration limits now. Now coming to the limits. Coming to the limits. Okay. Now when small r is equal to 0, small r is equal to 0, then what will be t? T is equal to x. T is equal to x. Put r is equal to 0 here. R is equal to 0. If I substitute r is equal to 0, then t square is equal to x square, which means t is equal to x. That means in place of 0, we have this integration in terms of dr, but here we have the integration in terms of dt. The limits must be, the upper and lower limits of the integration must be changed according to the integration factor. So here we have r is equal to 0. For r is equal to 0, t is equal to x. T is equal to x. For r is equal to, capital R can be extended to capital R, and we have upper limit as capital R. If r is equal to capital R, if I put capital R in place of small r square plus x square is equal to t square. R square plus x square is equal to t square, is equal to t square, is equal to t square, right? Now r square plus x square whole to the power. Now if I put r, now t is equal to how much? R square plus x square whole to the power 1 by 2, which is root, Now I know the lower limit, which is x. I know the upper limit as well, which is r square plus x square whole to the power 1 by 2. R square plus x square whole to the power 1 by 2. 1 by 2. Is it clear till now? Right? I'm going to take this entire thing out. Okay? Right. Now, so as I've got the integration limits, I'm going to solve this integration entirely. Now, E is equal to sigma 2 epsilon naught are constants. X is also constant. I'm keeping all those things as it is. Now, as I have 1t and as I have t square, integral 1 by t square dt from x to r square plus x square whole to the power 1 by 2. 1 by 2. Now, as I know, 1 by t square integration is minus 1 by t. Minus 1 by t. See, this t square, 1 by t square can be written as t to the power minus 2. So, d by, integration, right? Integration of t to the power minus 2 dt is equal to t to the power minus 2 plus 1 by minus 2 plus 1. T to the power minus 2 plus 1 is t to the power minus 1, minus 2 plus 1 is minus 1, that means minus 1 by t. Minus 1 by t. So, 1 by t square integration is minus 1 by t. So, that is equal to sigma x by 2 epsilon naught minus 1 by t from x to r square plus x square whole to the power 1 by 2, 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 1 by 2. Now if I substitute the limits, first I'll substitute upper limit minus lower limit. So minus, I'm taking it out, minus sigma x by 2 epsilon naught. First upper limit 1 by r square plus x square whole to the power 1 by 2, whole to the power 1 by 2 minus 1 by x, minus 1 by x. I'm just trying to adjust within the means that I have the space. Okay. right? Now E is equal to minus, I'm multiplying sigma x by 2 epsilon naught, sigma x by 2 epsilon naught. When I multiply the minus, I will get 1 by x minus 1 by r square plus x square whole to the power 1 by 2, 1 by 2, right? Now I have x here, x can be multiplied, so E is equal to sigma by 2 epsilon naught, 2 epsilon naught. When I multiply x, x by x is 1 minus x upon r square plus x square, sorry, r square plus x square whole to the power 1 by 2. So this is the equation for the electric field intensity at a point along the axis of a uniformly charged disk. Uniformly charged disk. When you look at this equation, sigma is the surface charge density of the disk, epsilon naught is the permittivity, permittivity of free space, and x is the length along the axis from the center of the disk, r is the radius of the disk. Okay, so this is a very good final result, which is E is equal to sigma by 2 epsilon naught 1 minus x by r square plus x square whole to the power 1 by 2. In some books, it will be represented as E by 2 epsilon sigma by 2 epsilon naught 1 minus x by root r square plus x square. Both are correct because power 1 by 2 will be treated as square root, I think the steps or the explanation that we have followed through till here, till this equation, are very clearly understandable. Okay, if you are still unable to follow, just comment below. I suggest you watch it two to three times. You will be able to follow it, you will be able to solve the problems based on this concept. Okay, and one more point that I wanted to mention is, not many questions have been asked on this concept. Anyhow, it is always better to learn surface charge density, linear charge density, and volume charge density examples, because we don't know when and what kind of questions will be asked in mains or advanced or even in NEET. Okay, right? So yes, let's move on to the examples. Okay, now let's move on to some different cases which are important cases. Okay, now, okay, right. So this is the disk. This is the disk. I'm naming it as disk of surface charge density sigma. Of surface charge density sigma. At a point. Now this is the axis. This is the axis, and we have determined the electric field at point P is sigma by 2 epsilon naught 1 minus x by 1 minus x by r square plus x square whole to the power 1 by 2. Right? This is the expression that we have derived in the earlier slide. Okay. Now the special case is, let's say this disk is infinitely large. Infinitely large. What do you mean by infinite? Infinite is a relative term, as I've already told you. Infinity is a relative term. For example, I have taken this size of disk. This size of disk. Now I have considered an axis here. Axis here. Now let's say this disk is a bigger one, something like this disk, and the axis that I've considered is this one. Axis that I've considered is this one. I can say this disk is infinitely large. When can I say this disk is infinitely large? When the point of observation, the point where the electric field we are measuring, is very close to the disk. When we are here at this point, when we look at the disk, it will appear bigger. It will appear bigger. As we move away, it will appear smaller. Okay, so I can say this disk is infinitely large when we consider the point very close to the disk. Very close to the disk. That means the x value is very less as compared to the radius of the disk. As compared to the radius of the disk. Now I'm taking the case of I'm taking the case of infinitely large disk. That means this x is very small when compared to r, right? So this is the disk that I've taken, and this is the axis. I've considered the point here. This x distance is this one, r is this one, x is very much less. Sorry, x is very much less than capital R. X is very much less than capital R, right? Now, let us say x is very much less than capital R. What happens to the equation? E is equal to sigma by 2 epsilon naught. 2 epsilon naught 1 minus x by r square plus x square. R is very much greater. So, r square whole to the power 1 by 2 x by r. What am I getting? X by r. But instead, this is not that important anyway. But instead, let's say you are told that the disk that we have considered is infinitely large. What happens in such a case? So listen to me very clearly. So this disk is infinitely large. Disk is infinitely large. Disk is infinitely large. Disk is infinitely large. That means r tends to infinity. R tends to infinity. R tends to infinity. If I put this case in this formula, what happens? This electric field E is equal to sigma by 2 epsilon naught, which comes as it is, 1 which is also there, which will not change, x is again same, but here what do we have? R square. R is infinitely large. If R is infinity, R square is even more. So R tends to infinity means infinity square. Infinity square is again infinity. Anything by infinity will result in zero. Am I right? Yes. Okay. So E is equal to sigma by 2 epsilon naught. Here I have discussed this concept of infinitely large sheets or disks briefly, right? We will learn about this concept in the later lectures in a detailed manner. Okay, but for now, however, the result would be same. Sigma by 2 epsilon naught is the electric field intensity of an infinitely charged sheet. That sheet can either be in the shape of circle, that sheet can either be in the shape of rectangle, that sheet can either be in the shape of a square. Okay, whatever the shape that it has, it is an infinitely large charged sheet. So in such a case, the electric field intensity is sigma by 2 epsilon naught. What is sigma here? It is the surface charge density. How do we define this surface charge density? Charge distributed per unit surface area. We will also derive this equation by using Gauss law in the later lectures. But anyhow, for now, you just need to remember this. E is equal to sigma by 2 epsilon naught. Where do we use this E is equal to sigma by 2 epsilon naught? Infinitely charged sheets. In parallel plate capacitors. So parallel, if we take a parallel plate capacitor, something like this, okay. So this is a parallel plate capacitor. What is the element of parallel plate capacitor? This parallel plate capacitor can either be of rectangular sheets parallel to each other, or of circular discs parallel to each other, or square sheets parallel to each other, or infinitely larger, whatever the shape of sheet is. It is infinitely large. Two sheets are being separated parallel to each other, separated by a small distance. Let us suppose the surface charge density of one sheet is plus sigma, and the surface charge density of the other sheet is minus sigma. This is how the capacitors are made of. Two metallic sheets, thin sheets, are placed opposite to each other. This combination is called parallel plate capacitor. Now, what is the electric field? Due to this plate? away from the sheet, away from the sheet. How much is it? It is sigma, sorry, it is sigma by 2 epsilon naught in this direction, in this direction, pointing away. As this is minus sigma, right? What is the electric field at this location, in between the two plates? In between the two plates, one field is pointing in this direction. What about the field of this one? As I've already told you, electric field always points towards the negative charge, away from the positive charge. That means the field due to this negative charge also in this direction, right? So I'm writing sigma by 2 epsilon naught in this direction again. Both the fields are in the same direction in between the two plates. In between the two plates. Now what is the net electric field? E net is equal to, as both the fields are acting in the same direction, we can add them directly. 2 sigma by 2 epsilon naught, which is 2 will get cancelled. E net between the two plates of a parallel plate capacitor, which is sigma by epsilon naught. This is a very good result which we use in the analysis of parallel plate capacitors. Okay, so what we have discussed in this lecture is, we have derived the equation for the electric field intensity along the axis of a uniformly charged circular disk, of a charged circular disk, and we have we have used some different cases of the electric field due to circular disk. What if the circular disk is infinitely large? Is infinitely large. That means the radius of the circular disk is infinity. If the radius of the circular disk is infinity, then if I put r infinity in place of r, this entire term will become 0. Entire term will becomes 0. So we will get the conclusion for the electric field intensity due to an infinitely large charged sheet. Charged sheet. As I'm seeing charged sheet, you can even say infinitely large charged disk, infinitely large charged sheet, infinitely large charged square plate. So which is E is equal to sigma by 2 epsilon naught. When we look at this formula, we will get a conclusion. This electric field for an infinitely charged sheet or a plate is independent of the distance. Is independent of the distance. That means what? That means what? As this disk is infinitely large, then what if wherever you are measuring the electric field, it will give you the same result. It will give you the same result. So if I have taken a charged sheet, then the electric field at this location is sigma by 2 epsilon naught. Electric field at this location is again sigma by 2 epsilon naught. Electric field at this location is again sigma by 2 epsilon naught. That means if this is the case of uniform electric field intensity. Uniform electric field intensity, which has been given by infinitely large sheet, infinitely large, infinitely large charged sheet. Okay, so these are the points that we have learned in this lecture. I hope the lecture or the explanation in this lecture is clearly understandable. Let's look at one more example. Okay, so this is the electric field, electric field at the center, at the center, at the center of a charged hemisphere, hollow hemisphere, charged hollow hemisphere, charged hollow hemisphere, hemi hemisphere. Okay, so this is the quantity that we are going to derive. Okay, let us draw the charged hollow hemisphere. Okay, now, okay, so this is the charged hemisphere. Sorry, I'm going to draw it again. So this is the charged hollow hemisphere. Okay. Now the center of this charged hollow hemisphere is this one. I'm drawing the axis. So these are the axes that I have already represented. Now, so this is the hollow hemisphere which is charged. The surface charge density of this hollow hemisphere is sigma. Let it be. What is it? Sigma. Now what I'm going to do is I'm going to divide this hollow hemisphere into concentric rings. Concentric rings. When we use the common sense, uh, this hollow hemisphere is composed of concentric rings. Concentric rings. See, so this is one ring, and the other one is this one, and the other one is this one, and the other one, and the other one. So this is how no hollow hemispheres are formed. Okay, right. Now what I'm going to do is I'm going to consider a small elemental ring in this hollow hemisphere. Okay, now to consider this element, what I'm going to do is I'm going to an angle theta. I'm going to an angle theta and take an element of thickness d theta. What is it? D theta, and its length is dl, and charge on it is dq. Charge on it is dq. How does the element appears? It will be a ring. It will be a ring. It will be a ring of thickness dl. Of thickness dl, and charge on this small element is dq. Charge on this small element is dq. Okay. Right. Now, let us assume the radius of this hemisphere is r. Radius of this hollow hemisphere is r. Now, if this is r, this also should be r, right? If this is r, the entire radius also should be r. So, if this is r, we can resolve this r into two components. We can resolve this r into two components. One is, I'm going to draw this diagram separately. Okay. So this is the element that I have considered. Okay. Now this is the center of the ring, and here we have, this is O. We need to find the electric field at this center, right? Now I have this as R, right? Now how about this component? If this angle is theta, this angle also should be theta, right? Now if this angle is theta, how will we get this value? R cos theta, right? And what about this one? R sin theta, right? Right? Now when you look at this diagram, if you turn this diagram horizontally, then the arrangement will be something like this, right? It is a similar diagram for us, because we have already learned the electric field along the axis of a circular ring. So this diagram just appears as the ring with axis. So to find the electric field at this location due to this ring, I'm going to write the equation here. The electric field at this point, electric field at this point electric field at this point due to this ring, this r sin theta is nothing but x, right? Length along the axis. And this r cos theta is nothing but radius, the charge is dq, charge is dq. These are the things that we require. So I'm going to write the equation for the electric field intensity at this point at the center due to this ring, so dE. So ring is small elemental ring that I have considered small element part. So it creates a small amount of electric field. That electric field is given by this equation. dE is equal to K charge dq kq x is how much? R sine theta, r sine theta x kqx by r square plus x square, r square radius square, which is r cos theta whole square plus x square. X is nothing but r sine theta, which is r sine theta whole square, whole to the power 3 by 2, right? So I'm going to write the equation for the electric field along the axis of the circular ring, which is E is equal to K Q x by r square plus x square whole to the power 3 by 2. This is the actual expression. When you look at this diagram, here x is the length along the axis, which is r sine theta. I have used it here, r sine theta. And what is the charge of this elemental ring? This is dq. I have used dq here. K is Coulomb's constant. It comes as it is. Now r square. R is the radius of the ring. So here the radius of the ring that we have considered is r cos theta. I have used r cos theta, okay, square plus x square. X that I have already mentioned, r sine theta square. Whole to the power 3 by 2 is there, that I have written over there. Okay, so let's erase this one. Now what we are going to do? dE 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 is equal to K dq. How do we write this dq? We know sigma is equal to q by a, which is equal to dq by dA. If I want to find a dq is equal to sigma dA, right? Sigma dA. In place of dq, I'm writing sigma dA r sine theta divided by r square cos square theta, r square sin square theta. If I take r square common, cos square theta plus sin square theta is 1, then r square I'll get. R square whole to the power 3 by 2 means this 2 will get cancelled. I will get r cube. I hope the calculation of this part is clear, right? Okay, now we have r here, we have r square here, I mean r cube here, that we will get r square. Now let us find dA. What is dA? dA is the area of this entire ring, right? Entire ring. Ring area is nothing but length into thickness. What is the length of this ring? 2 pi r. dA is equal to length into thickness, right? Length is how much? 2 pi. Radius is r cos theta. 2 pi r is its length, and thickness is what is the thickness? dl. Thickness is dl. So this is the area. Now if I write the equation correctly, dE is equal to K sigma. dA can be replaced with what is it? 2 pi r cos theta dl. 2 pi r cos theta dl. Into sin theta divided by r square. 1 r we have in the numerator, 1 r square we have in the denominator. They will get cancelled out, and I know this k value. K is nothing but 1 by 4 pi epsilon naught. So 2 pi 2 za, right? Okay, now dE, what is it? dE is equal to I have 1 by 2 epsilon naught, sigma by 2 epsilon naught 2 pi gets cancelled, r is also not there, sin theta cos theta, sin theta cos theta. What I'm going to do is I'm going to multiply with 2 and divide with 2. So what am I getting? Here I'll get 4 epsilon naught 2 sin theta cos theta into dl, right, by r, by r. Is everything clear till now? Right? Okay. Now now this dl can be written as, can be written as this dl can be written as, dl is the arc length, right? Arc length can be written as radius times angle, radius times angle. So this 2 sin theta cos theta can be written as sin 2 theta, can be written as sin 2 theta, and dl can be written as r d theta, r d theta, because dl is the arc length, right? Arc length can be written as radius times angle, r d theta, r d theta. So if I rewrite this equation, what am I getting? dE is equal to sigma by 4 epsilon naught, sigma by 4 epsilon naught. I have sin 2 theta here, sin 2 theta, r and r will get cancelled, this r and this r will get cancelled. So what do we left with? Sin 2 theta d theta, sin 2 theta d theta, right? So this is the electric field due to this small elemental ring, elemental ring. Now to find the electric field at the center due to the entire hemisphere or hollow hemisphere, what do we need to do? We need to integrate, we need to integrate. We know this entire terms, this entire term comes out to be net electric field, net electric field is equal to, sorry, net electric field E is equal to sigma is constant, 4 constant, epsilon naught is also constant. What is the integration of sin 2 theta? Before doing the integration, we need to apply the limits also. We need to define the limits also. How do we define the limits? What are the limits? Lower limit and upper limit. So this, hollow hemisphere is extended from here to here, right? So if I take the ring here, it will be covering the entire ring like this. If I take another ring just above it, it will be covering the entire ring from this side and this side. If we take another ring above, another ring above, another ring above, each ring is covering this side and this side. So how do we take the limits? Lower limit is 0, obviously. Lower limit is 0. And what will be the upper limit? Upper limit is 90 or 180? 90 or 180? Which one is correct? It should be 90. It should be 90 because it should be 90 degrees, because when we take the ring, it is covering both sides. It is covering both sides, 0, 30, 45, 60 and 90. 90 is again covering both sides. Ring is covered on both sides, right? So if I take 0 to 90, means this 0 is covering this portion also, this 90 is covering this portion also. That means if we take the limits from 0 to 90, it would give the net electric field of this portion, entire portion of the hollow hemisphere. Okay, right. Now sin 2 theta integration is minus cos 2 theta by 2 from limits 0 to 90 degrees. 0 to 90 degrees. Okay, so E is equal to sigma by 4 epsilon naught, 4 epsilon naught, 1 by 2 is here, 1 by 2 is here. As we have negative sign, this limits can be reversed, or even you can use the regular substitution also. I'm using the regular substitution. Minus cos 2 times 90, theta is 90, right? Cos 290, 2 times 90, 2 times 90 is 180, cos 180 is minus 1, cos 180 is minus 1, minus minus plus 1, minus minus plus 1, and we have this negative, and we have negative sign, so total together plus. Instead what we do is, let's do this separately. I am keeping the negative sign here. negative sign here. I'm substituting the values. Cos 180 is minus 1. Cos 180 is minus 1 minus cos in theta we should place 0. 2 times 0 is 0. Cos 0 value is 1. Cos 0 value is 1. This is minus 2. Minus 2 times minus is plus 2. Plus 2 plus 2 will get cancelled. What do we have here? E is equal to sigma by 4 epsilon naught. So this is the expression for the electric field at the center of a hollow hemisphere, charged hollow hemisphere. Okay, I hope the entire analysis is clear. Entire analysis is clear, right? I hope you have understood all the steps and the explanation that I have followed through. Okay, this is a very good, very important result. Although this, I mean, not many questions have been asked in this on this concept, but anyhow, it is always better to learn more and more, more and more. So these are the two concepts that we have learned. We have seen different cases, like if the disk is extended to infinity, it will act as a charged sheet, thin sheet. Then the electric field intensity is sigma by 2 epsilon naught, which is uniform everywhere. Uniform everywhere. Okay. So yes, I hope this lecture is helpful to you. If you find the lecture is helpful, please do like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. That's it in this video. Thanks for watching. See you in the next video.